Hello everyone, it's Student Dave. How's it going? So this is the MATLAB implementation of the kalman filter based multi-object tracking, which was based upon the detection I did in the last in the last video tutorial. And in order to really understand this, make sure you watch the video where I explain how all this works, because here I'm just kind of showing you how the MATLAB code works. Okay, so basically what we're going to do is we're going to load in the images. This is just kind of showing what we're going to look at, but we're just going to load in the images. And then we're going to set up all our initializations for the kalman filter. And so what makes this a little bit different than the object tracking we did before is that we have multiple objects here, and we have an unknown number of objects and a unknown number of detections. So we know when they overlap, we might get more or less detections. And so what we need to do is have some way of dealing with that. And so by treating every single detection as a potential estimate, we're going to go, okay, so we have all these detections. Like say we get 5 detections. Let's say these are estimates. These are 5 estimates. Let's follow them into the next frame, and the next frame, and the next frame. And if any detections aren't getting assigned well, that is, they're the closest assignment's very far away, and we just ignore it, we're just going to go, okay, this detection didn't work out, get rid of it. But what allows us to do is that every time there's a detection, we get an estimate. We basically create it as a candidate for a fly. And so anytime we see something, it'll start to track it. If a new fly comes in or a fly leaves, we'll be able to say, okay, this might have been a fly, follow it. Oh, it's not a fly, get rid of it. And so it allows us to dynamically not have a set value of the number of flies, but allows us to query each time and then apply some decisions about whether or not we should keep it, or if it's worth tracking as a fly. So here's how I define it. This is just basically creating in this case I initialized it to the number of detections in the first frame. We have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I guess 10. And so that's what we're going to start off with, but it could vary as we go. So let's just, and I don't want to start off with the very first frame. I guess I could have, but whatever. We'll just start off with, I called it S frame. I guess that's frame 5, no big deal. Then we load in the image, and we're going to load in the image, and we're going to load in the particular coordinates for all the detections. So this is the X and Y coordinates for all the detections in that particular frame. Then what we're going to do is we're going to do the kalman filter. And so what I do is I take the number of estimates we have. Here our number of estimates is 11. Okay, it wasn't 10, it was 11. And I'm going to update all those estimates. So what this says is that here's our detections. In the next frame, where do we think they're going to be next? Clearly, because we just have one data point, the estimates aren't very good. But, we've got to start somewhere. Then we do our kalman game and prediction. And now what we're going to do is we're going to do the Hungarian algorithm. So we have our estimates. We're in the very first frame, so estimates are going to be exactly equal to our detections. But as we go forward, our estimates are going to move, right? We have these detections, and now we have these estimates, and now our estimates in each frame is going to move and move and move. And they're going to move based upon the prediction from the kalman filter. So for the next frame, for example, we'll have some estimates, and then we're going to have some detections. And like I said, we want to match them up. So what the Hungarian algorithm is going to do is it's going to align them the best that it can. Our cost measure is how far away are each of these points from each other. And so what we do is we get the pairwise distance between all the detections and all the estimates. So that'll create this. And then I limit to just some subset of that quadrant, and this will create it here. So what we get is this. Let me just draw that out. We're going to get this. This allows us to create the matrices of all pairwise comparisons. So this is basically our giant cost function. This is our cost metric, our cost matrices for all the pairwise distances between each of the points. And this is what we're going to input to the Hungarian algorithm. And what that's going to do is going to optimally assign these pairs, saying we got our estimated positions, we got our detected positions. Let's match them up the best we possibly can and see how that does. So we go ahead and do that. This is the program. I'll put a link to the program on the website. It's in MATLAB Central. There's a lot of different Hungarian algorithms. I like this one a lot. It deals with also rectangular, because we don't always have the same number of detections as we do estimates. So this is a nice one. And then so now we got our assignments. So let's look at our assignments. We got our assignments and we got our costs. So this is assigning each estimate to some detection. This is what we get here. Then we're going to run through some checks. We're going to say, well, we're actually just going to do one check. We're going to go, okay, so we did assign everything. The program's not going to not assign. All of them are going to get assignments. And so well, maybe some of those assignments aren't any good. Maybe the distance between these points is way too far, and while this program does align the best it can, there's some that just might not be worth tracking. And this allows us to do that, and I set the threshold at 50, a distance of 50 away. Okay, then now that we got all our assignments, let's apply those assignments to the update. So now we're going to take each detection that's matched with a particular estimate and do the update for that one. So basically use that best candidate detection to update our estimate. Okay, we update our covariance matrices and we store the data. Now, the next part is that, okay, let's see if we have any new detections, because we may not have been able to assign all the detections. And let's take a look, see which ones are new, and if they haven't been assigned, let's say we got a new candidate, this might be a new fly, let's keep that fly. So I run this. Then we say, okay, also by the way, any tracking that didn't get matched to a detection, they're going to get a penalty. We're going to count those penalties. So for every single detection we get throughout time, throughout all these frames, we're going to keep counting every time one didn't get a detection this time. And so if a particular estimate goes some number n with no detections, we're going to go, you know what, we've lost the fly, or maybe this never was a fly, and get rid of it. So we run this part of the code. This increments that strike tracking. And then in the next line, anything that got a bad track, anything that's got a 6 or higher, we're going to wipe it out. Now, what that's going to do is basically create, in these matrices, we're going to have a bunch of candidates that go through time. So we're going to get one new fly, another new fly. And we're going to basically stop ones that got a value of 6 and say that track is done for, let it go, never again. And then we can plot the data here, and this is a nice way for plotting it. And that's pretty much it. That's the whole code. It's really not that involved, and I'm sure for a lot of cases this won't work, but it does a very good job for a pretty complicated situation where you have animals moving in unpredictable ways. It's biological motion. It's not a ball flying through the air. It doesn't have very well-defined trajectories and motions and accelerations. And there's a lot of overlap, and sometimes there's 3 of them overlapping at once. And so it does a pretty good job for that. So I don't know how well it does for a lot of generalized cases, but it seems like it does pretty well for anything we can get a good blob estimate of, like a car or a person, because people definitely aren't going to move around like these flies will. Okay, so let's just take a look at it real quick. Boom. Okay, so first frame, useless. The detection is the exact same place as the estimate. And there we go. So it has to track them. And I just add this little tail on for fun. And you can see here's the tracking, right? So let me just give an example. Like say here, the 2 flies are crossing. The estimate for this pink one is going to be here next, somewhere up this way. Whereas the estimate for the red one is going to be here somewhere. And so because of that, in the next frame, we're going to have detections at these 2 new locations. We have and not just here, but for all of them, we have all these detections, which are the red circles, and we have our estimates, which are the lines, and are the end of these lines, and we're going to go, okay, which ones let's arrange them optimally, and anything that's far away, get rid of it. And so even if our estimates were pretty bad, say this estimate here said, oh, we're right here, and this one said, oh, we're right here, because we're forced to assign everything, there's no way this one over here is going to get to be that candidate, or these. And so the best candidate, even though the estimate's off, is going to be this guy and then this guy. And that's why it's robust. Like, even though this estimate system is completely awful, because I'm using a constant acceleration model, I mean, that's no good. These animals definitely don't have constant, so this is not a ball flying through the sky. But it does surprisingly well because our Hungarian algorithm forces an assignment. In certain situations, it's going to fail pretty bad, but by and large, for this case, it works decently, I think. I mean, who knows? Everything's kind of relative here. Anyway, so yeah, here's the code. I'm gonna put it on the website, and it'd be really cool if you guys could tweak it and then maybe post it back, or maybe message me and I could post it on the website to see how good something like this can actually get, and maybe we could really, make some kind of cool paper about how flies move around. That stuff's pretty popular nowadays. Okay, all right, see you guys.